Two balls as per our convenience. Maybe they are of same color or whatever the given event is. So basically, mota moti karke, by and large, there are only two things: number of cases of favorable events, number of cases of total possible outcome. Basically. Okay. So let me screen share. Are there any doubts? No doubts. Okay. So let's start with the question. Okay. The question is, in a collection of 6 English books and 4 Hindi books, the probability that 3 particular English books will be together is what we need to find out. Okay. So we have 6 English books and 4 Hindi books. In total, we have 10 books. So how many cases in which we can arrange 10 books, and we are like putting every book like this: one book, the second book, third book, fourth book, like this. Okay, vertically. Okay, so we have total 10 books. So total number of cases is 10 factorial. And there are 3 particular English books which needed to be staying together. So whenever there is any case of togetherness, we take a box and we'll make as many places, as many elements are there to be arranged. So 3 books, 3 places, 3 places, 3 books to be arranged. How many ways? 3 factorial. This is a box having 3 particular English books. How many books are remaining now? If 3 English books are in the box, so 3 English books are remaining and 4 Hindi books are remaining. So how many total elements to be arranged? 4, 3, and this is the one element. This is a box. 4, 3, 7 and 1. 8 elements are to be arranged. So how many total ways are possible here of arranging them? 8 factorial and multiplied with 3 factorial. That is the number of ways to arrange 3 English books inside the box. So that's the total number of ways of arranging let me first make space. Number of ways of arranging 3 particular English books. And now 3 particular English books is means that there are 3 English books already selected, which are to be arranged out of 6. It's not that we have to select 3 books, any 3 books, any 3 English book. No, it is particularly given. So we need not to select 3 books from 6 because they're particular. Now, please heed every word changes the question for you. If it was given that if any 3 English book can be should be arranged together, then we have to first select 3 books out of 6, and this also will get multiplied with the number of cases, but not now in this case because there are no any three particular there are no three any three English books, but there are 3 particular English books which are already selected, which has to be together. That is the difference. So number of ways of arranging 3 particular English books is this: 8 factorial to 8 3 factorial, where 3 where 1 is a box, 3 English books are remaining, 4 Hindi books are remaining. So total elements do we have 8 elements to be arranged, and in the box itself has 3 factorial number of cases to be arranged in different manners. Is that clear? Is this number of ways clear?
Yes, sir.
These are the number of cases to our favorable event. So let's bring them here then for the probability of event. 8 factorial cuts 10 factorial by 10 into 9. 3 factorial is 6. 6 by 3, 2. 9 by 3, 3. 2 cancels 10 by 5. Probability of event is comes out as 1 by 15. That is our answer. Clear?
Yes, sir.
Okay, so let's assume that you have prepared hard and you are in the academy. There is a question for you. There are n cadets that have to stand in a row. If all permutations are equally likely, then the probability of two particular cadets standing by side is what we have to find. So let's solve. There are n cadets have to stand in a row. Okay. So this is the event that is happening for sure. No, it's happening. Engine. Save it. Let me save the file. So see, there are n cadets that has to stand in a row. So how many total arrangements can be made? N factorial. This is the total number of ways. Favorably, we want to discuss the cases where 2 particular cadets are standing by side. So if they have to be together, we'll make a box. There are 2 elements, 2 places. 2 elements, 2 places. How many ways to arrange? 2 factorial. There is a box in which there are 2 candidates, in which there are 2 cadets. How many cadets are remaining? 8 cadets are remaining. So 8 cadet in a box. How many elements to be arranged? 9 factorial. Sorry. There were not there are n cadets. 2 are inside. How many are remaining? N minus 2 are remaining. N minus 2 cadets and one cadet, and sorry, n minus 2 cadets, and a box is to be arranged. So n minus 2 plus 1. These are the total elements which has to be arranged, and 2 factorial is the number of cases to the box. The box can have 2 factorial ways to be arranged because there are 2 cadets inside it. Is this point clear till now?
Yes, sir.
Here we are arranging a box and n minus 2 cadets. So how many total elements? N minus 2 plus 1 box. That is n minus 2 plus 1 becomes n minus of 1 factorial into 2 factorial. Now these are the number of favorable cases to our event. Okay. If it is so we'll write it here. Now n factorial can be written as n into n minus 1 factorial. N minus 1 factorial is there in the numerator. So wow, cancels. 2 factorial is 2. 2 by n is our answer. Is that clear?
Yes, sir.
Great. So let's now move ahead and let's discuss something else. There are so many examples we have discussed. Do you remember what is De Morgan's law? Anyone? From sets chapter. The number of elements in set A union B, complement of the complement of union set is can be written as A's complement intersection B's complement. So you can just simply replace n with p. Probability of this particular set can be written as clear. What we have done, we have simply divided it by number of sample space, number of elements in sample space. That has become the probability. As simple as that. That's the application of De Morgan's law in probability, and it goes for both of the side. Okay, and like the De Morgan law also says here also probability with the complement of intersections here, and then as probability of any doubts, anyone? So just when you will finish the chapter, you will feel what sets are, and then what is a complement. Then you will be able to better understand. Okay. For now, it's just like a property. Are there any doubts?
No, sir.
Okay. Now let's discuss conditional probability. Important topic. Conditional probability discusses about two events. In this particular topic, we'll discuss about, like, let's say there are two events, A and B, and both of those events are going to happen. Like, they are not impossible events. Okay, so if we have to find out that if A has taken place, then what are the chances of B taking place in that scenario? So probability of B when A has taken place is represented by this. This is simply probability of event B when A has occurred. Or if I write probability of A, this means that probability of occurrence of event A when B has taken place or occurred. So now when we are writing these definitions, then via these definitions only, we are able to understand that somewhere A and B has to affect each other, then only the conditional probability has any role in it. So here, mostly A and B events are dependent on each other. If they are dependent on each other, then only the probability of other event depends on the probability on the occurrence of the other event, right? So that is what the topic is about. Let me read the definition from the book, and let me write it also for you. Let A and B be two events such that probability of event A is more than zero, means it's not an impossible task, then probability P of BA denotes the conditional probability, of event B given that A has occurred. Since A is known to have occurred, it becomes the new sample space replacing the original sample space, from where we can write that the probability of event B given that A has taken place is probability of A event occurring simultaneously with B divided by the probability, or we may say increased by the probability of A event being taken place. Here, we know that the probability of any event lies between 0 and 1. So if it gets divided by anything, and if the probability is getting divided here, so it's basically increasing its chance, its odds. This is known as the conditional probability. Event B given A. Is that clear, everyone?
Yes, sir.
Yes.
Yes, sir.
So for independent events, yeah, my writing. For independent events, probability of occurring both of the events was simply the multiplication both of their probabilities because their occurrence were not interfering the other event. So if that is so, then we may write, let's write it on the next page. That is so, then we may write for independent events that the probability of event B given A has taken place will be probability of A intersection B divided by probability of A as per the formula. Probability of A intersection B is what? P of A into P of B in the case of independent events. So probability of event B given A has taken place is just equal as the probability of B. Or similarly, we can write probability of A given that B has taken place will also be equal probability of A for independent events. So that's why the conditional probability as a concept is important for dependent events. Is this clear that how have I written so? No or yes? Hello everyone. Is there any doubt? Please ask if there is any.
No, sir.
No?
No, sir.
Okay, let's go ahead and discuss an example now. Two dices are thrown. I don't know who are these people throwing dices all the time. What do we have to discuss? An example. Two dices are thrown. Find the probability that the numbers appeared. That the numbers appeared has a sum of 8. If it is known that the second dice always exhibits 4. That is the case. Let me reread it again for you. That two dices are thrown and we have to find the probability that the numbers that appeared on both of the dices has a sum of 8. Just the favorable event. If it is known that the second dice always exhibits 4. So the given event, it is known that this is the given event. Okay, let's call it as A. Sorry. Let's call this event as event A. Okay. So how many cases are there for event A? So if there are two devices, there is always 4 on the second. There can be 1, there can be 2 on the first device, dice 3, 4, 5, and 6. So basically, 6 cases are there for event A, where like 4 is there always on the second dice. So that's the event A. Let's call our favorable event that the numbers appeared has a sum of 8 as event B. Okay. Now event B having having the sum of 8. Okay. So 1 7, no, 7 is not possible. 2 6 is possible. 3, 5 is possible. 4, 4 is possible. 5, 3 is possible. 6, 2 is possible. 7, 1 is not possible. So how many cases? There are 5 cases. Okay. And as per our formula, as per the question, we have to find out the probability of occurrence of event B when A has already taken place. So for that, we need to find out probability of A intersection B and the probability of A. So we don't care about event B, just we care about is A intersection B. So what is A intersection B? Can you tell me? Both of the sets are there in front of your eyes. Please tell me. Come on, speak. It's just a simple question. You have to find out the A intersection between sets A and B. Both of the sets are written in front of you in roster format. You just have to tell me the common element, which is a common element in between these two sets. 1, 4, no. 2, 4, no. 3, 4, no. 4, 4, yes. 4, 4 is common in both of the sets. 5, 4, no. 6, 4, no. Okay. So this is the only element common. Okay. Now finding out the probability. 1. How many total cases are there? 2 dice are thrown, so 6 square divided by, how should I write it? Divided by the probability of A. How many total favorable cases are there in A? 1, 2, 3, 4, 5, and 6. 6 divided by 6 square. Okay. 1 by 6 square. 6 square by 6. This cancels. 1 by 6 is our answer. Is there any doubt, anyone?
No, sir.
Event B was getting a sum of 8. Event A was getting 4 on second dice. And we have to find out the probability of event B and we have to find out the probability of event B when A has taken place. Okay, so that's why we'll apply conditional probability formula because A has taken place. It is the given in the question that if it is known that the second dice always exhibits 4, it is known. So we have considered the probability of occurrence of event A and B simultaneously having a sum of 8 and getting 4 on the second dice. That's the only single element 4, 4, which is there in the set. 4, 4, okay. 1 divided by total number of cases. Total number of cases when 2 dice are thrown are 6 square. Divided by the probability of event A. There were 6 elements in event A and total number of cases 6 square. So, calculated, hence we got the answer. Is there any doubt, anyone?
No, sir.
Let's discuss some more examples. Will be because this particular concept, this particular topic is very important for the end. A bag contains 3 red, 6 white, 7 blue balls. 2 balls are drawn one by one. Are drawn one by one. What is the probability that the first ball is white and second ball is blue when first drawn ball is not replaced in the bag? That is the question. There is a bag, so let's make a bag. 3 red, 6 white, 7 blue balls are there. 2 balls are drawn one by one. One ball is drawn, thereafter, second ball is drawn. What is the probability that first is white and second ball is blue when first drawn ball is not replaced in the bag? Okay, so let's name the event of drawing first ball as white as A, because it has already given us it is taking place first, and then we have to talk about the probability of the second. Actually, no, it's not given like this. This spelling mistake. Two. Two balls are drawn one by one. What is the probability that the first is white and second ball is blue? It's not uh, given like that the first ball is white only. We have also have to discuss about the probability of being the first is white and the second is blue. So what we are saying is that first has to be white and then it has to be blue. So they are both dependent events. So simple fundamental principle of counting will be applied. So for withdrawing the first ball as white, how many total favorable cases? 6 divided by 3 plus 6, 9 plus 7, 16. Dependent event, so multiplication. Now, how many balls are there? There are 5 white balls remaining this time. We have to withdraw a blue ball. So 7 favorable number of cases. Now this time 3 plus 5, 8 plus 7. 15 balls are remaining. That will be the probability of our event. This is not a question of conditional probability. Why not? Because in conditional probability, there is certain event given as already taken place. But it is not the case here. We shall not get confused. 3 2s are 5, 3 5 are 15, 2 8 are 16, 7 by 8 5 are 40. That's our answer. Clear? And this particular event that we have written here, this is if we are calling first event as withdrawing white ball as A, and if we are calling event the second event when we are withdrawing blue ball as B, then this is the probability of event A multiplied with the probability of event B, assuming that A has taken place, because we have assumed here that the one white ball is already withdrawn. So this is this, but it's not exactly the question of conditional probability, but yeah, we can understand it like this, that this 7 by 15 is the probability of event B after event A has taken place. Is that clear?
Yes, sir.
Okay, so let's now discuss one more question on certain lines, on somewhat same. This time a bag contains 4 red and 4 blue balls. 4 balls are drawn one by one. So 4 balls are drawn one by one from the bag. Then find the probability that the drawn balls are alternate in color. What is the probability that drawn balls are alternate in color? Oh, typical question. So there has to be alternate in color. How many different colors do we have? Only two different colors are there, red and blue. Red and blue. And 4 balls are drawn. There has to be alternate in color. Okay, simple question. Let me set up. Give me a minute. Okay, is my voice audible?
Yes, sir.
Yeah. So there's a bag, 4 red, 4 blue balls. We are withdrawing 4 balls one by one. So 4 balls are being withdrawn. What is the probability that drawn balls are alternate in color? So how many choices of color do we have for the first place? How many choices? 2 choices. Okay. So the first ball can be red, but the next ball has to be blue because alternate case. The next ball has to be red or blue. Or the first ball can be blue, and then the next ball has to be red, next ball has to be blue, next ball has to be red. Okay, these are the two conditions. These are the two cases. Now, these are the two events that can happen. These are the two favorable events that can happen. Okay. So first so both of these are independent events when it comes to the fundamental counting of principle. And this time we are going to add the number of cases. Why exactly? Because why they are independent? Why they are, am I calling them independent? Because this event in itself is completing our case. What was our event? This was our event, withdrawing 4 balls. And this event is withdrawing 4 balls. Yes, it is doing so. So it's an independent event. Discussing about the next, this is also an independent event. This is also withdrawing 4 balls. So it's a complete event. So it's an independent event. That's where we are going to add the number of cases of both. But this time, we just not have to find out the number of cases, but also we have to discuss about the probability. So we are going to add the probability this time. Okay, let's call this event as E1. Let's call this event as E2. Probability of event E1 plus probability of event E2. What is the probability of event E1? So when we are withdrawing first ball, it has to be red. So how many total balls are there? 4 red, 4 black. So 4 favorable red colors are there upon 8. Okay, so this is the first ball with getting withdrawn. Now for the second ball, how many blue balls are there? 4 blue balls are there. Yes, there are 4 blue balls. That is absolutely correct. But this time the total number of balls are less. Why? One ball is already withdrawn. Okay, so 8 minus 1, 7 multiplied with. Now getting the third ball is red. One red ball has already withdrawn for the first. So how many red balls are remaining? 3 red balls. How many total balls are remaining? We have already withdrawn 2 balls. So out of 8, 2 are withdrawn. So 6 are remaining. Blue. How many blue balls are remaining? One blue ball has already been withdrawn. So only 3 blue balls are remaining. Out of 8 balls, 3 balls are withdrawn for this. So only 5 are remaining. So this is the probability of event 1 plus. Now discussing about the probability of event second. Withdrawing the first ball as black, blue. As blue. How many favorable cases? 4. Total balls 8. Multiplied with getting red ball as a second ball. So how many reds are there? There are 4 reds. How many total balls are there? After withdrawal of first ball as blue. So 8 minus 1, 7. Now withdrawal of the third ball as blue. We have already withdrawn one blue ball earlier, which was this. So there are 3 blue balls remaining. And total, after the withdrawal of 2 balls from 8, 6 are remaining. Similarly, for red, already one red is drawn, so 3 are remaining. After withdrawing 3 balls out of 8, 5 balls are remaining. Okay, so this is how the answer will be calculated. And as we can see here, so as we can see here the probability of event 1 and the probability of event 2, both of them are similar. So let's take common 4 into 4 into 3 into 3 in denominator, 8 into 7 into 6 into 5. Everything is common, so 1 plus 1 becomes 2. 2 cancels 8 by 4, 4 cancels 4, and what is left? 3 cancels 6 by 2. 4 into 3, that is 12, divided by 7 into 2 into 5. 2 cancels 12 by 6, 6 by 7 into 5 is 35, which is our answer. Let me check. Yes, it is the correct answer. Is there any doubt, anyone?
No, sir.
No? Yes. So this is how we are going to calculate the probability using condition, using our common sense and fundamental principle of counting. Okay. Let me repeat. 2 events. We are not referring to the slide. We are referring to any 2 events. A and B are said to be independent if occurrence or non-occurrence of one event does not affect the probability of the occurrence or non-occurrence of the other event. Then only we will call those events as independent events. In case of independent events, probability of A intersection B, that is the occurrence of both of the events simultaneously, will be given by the product of probability of event A into the probability of event B. Okay. But In the case of dependent events, let me write also. Where is my stylus? In my pocket. So in independent events, probability of A intersection B was probability of A into probability of B. That was the case of independent events. But if event B is dependent on A and A is dependent on B, let's say probability of A event has happened. Now, for dependent events, the equation is going to become that the probability of B when A has taken place. This is the case of dependent events. May be written otherwise also when B has taken place. When A and B are dependent events, where probability of B, A is the conditional probability of event B and A has taken place. The probability of A. And if you cross multiply left and right hand side, you will get what we have discussed right now once again. Okay, clear? Is this clear?
Yes, sir.
Okay, then I have some questions, mundane level questions. Probability of E event is 0.6, probability of F event is 0.3, probability of E intersection F is 0.2. We have to find out probability of E event when F has taken place, probability of F event when E has taken place. Now, any one of you, please apply the formula and go ahead and tell me the answer. Any one of you. Let me revise the formula also for you. Yeah, this is the formula. Intersection divided by A, whichever there is. Okay, now please enlighten me. Probability of E when B F has taken place. So should I write probability of E intersection F divided by probability of F, right? Which is given as 0.2 divided by probability of F 0.3. So 2 by 3 is our answer. For this time, probability of E intersection F divided by the probability of E, this is 0.2. Probability of E is 0.6, 2 by 6, 1 by 3. It's our answer. Any doubts?
No, sir.
Okay. Then let's consider a good question. A pair of dice is thrown. We have to find the probability that the sum is 10 or greater if 5 appears on the first die. This is what we need to find out. So, can anyone tell me, is this a question of conditional probability or not? It is, because it is given as the 5 appears on the first die. We are throwing 2 dices. Okay, so let's call this event as A. getting a sum of 10 or greater, let's call this event as B. Okay, for solution, we need to find out the probability of B when A has taken place. For this, we need to discuss about event A occurring with B and event A. So let's now just discuss about event A when sum is 10 or greater than 10. So a pair of dice is thrown. So 4, 4, 8, 5, 4, 9, 4, 5 also 9, 5, 5, 10. 5, 5, 10. 5, 6 is 11. That can also take. 6, 5 is also 11. 6, 6 is also 12. These are four cases in which the sum is 10 or greater than 10. Is there any other case? 6, 4. Yes, 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 yes. 4, 6 and 6, 4. And 3, 6, no. 3, 7, 6, 3, no, no, no. Okay. Yes, these are the only 6 cases in N of A. So probability of A is 6 divided by, if two pair of dice are thrown, 6 choices, 6 choices, 6 square are the total number of cases. 6 square, which is 1 by 6. A event and B event happening simultaneously. B, now A event says, sorry, this was B event. This was B. My bad. My bad. Okay. This was B event, and we had not to discuss about the probability of B event. This was B event. B event was as per our assumption that sum has to be 10 or greater than 10. So now if we consider A event which is getting 5. So getting 5. So let's directly write A event intersection B event. A event means that 5 should be there on the second dice. It is the case here. Yes. It is the case here. Yes. Only 2 events are there. Okay. So the probability of A intersection B is 2 by 6 square. And probability of A event is 2 by 6 square. Now probability of A event, sorry. Probability of A event is that we also have to discuss about probability of A event. Probability of A event will have 5 on the second dice and 1, 2, 3, 4, 5, 6 on the second dice. Sorry, 6 on the 6 cases are there on the first dice and 5 is fixed on the second dice out as outcome. So how many total cases are there? 6 divided by 6 square. This cancels. 1 by 3 is our answer. Any doubts, anyone? Is there any other doubt? Should I explain event A?
No,
What is
sir.
event A? Event A as per occurrence, as per assumption was that 5 appears on second dice. Okay, there are 2 dice is thrown. 5 is fixed here. How many choices are there here to fill? 6 choices. Here only 1 choice, that is 5. This is the only choice available. So 1 choice here. How many total cases are there? 6. 6 cases are there. 6 favorable cases divided by 6 square, that is 1 by 6. Probability of event A is 1 by 6. And the probability of event A intersection B was 2 by 6 square. Probability of hence A, not A, B when A has occurred will be probability of A intersection B divided by probability of B. A intersection B is 2 by 6 square and probability of A was 1 by 6. 6 cancels 6 square, 2 by 6, that becomes 1 by 3 is their answer. Clear? Any doubts?
No, sir.
Okay, that is clear. Are there any other questions regarding probability? No?
No, sir.
Okay, then shall we conclude our class?
Yes, sir.
Okay, then thank you everyone.
Yes, sir. Thank you, sir.